Okay. 10:30. Opening up my markers here real quick. And we are going to get right into it with an example that I did not finish last class. Did we have any slides here that I was missing? This is where I should start. Okay. A little bit of a review. I want to talk about particles, two force elements, and a frictionless pulley. Okay, so particle. Particle is a location without spatial dimensions and without mass. No moment can be applied to the particle, and it has to be in static equilibrium. Why I feel like this is really loud today. Okay. Particles, static equilibrium, some of the forces are equal to 0. Okay. Two force element or two force member has negligible weight. So if it is a small member and the weight is negligible compared to the forces being applied to it, we're not going to consider weight. Condition for it must only have two forces acting on it. In this case, it is force at A and force at B. Planar static equilibrium, forces are opposite, equal, and along the same line of action. So when I see this member AB, instead of resolving FBY and FBX and having a Cartesian coordinate system here, I can know that there will be a force on A and a force on B that are going to be along the same line that is member AB. They're going to be acting in the same direction. So the forces will be equal, opposite, and along the same line of action. Sometimes mathematically this helps us out. So keep an eye out for members like that when you're solving problems later on. Last thing we want to review is a frictionless pulley. Just changes the direction of the rope or cable, and it's connected to surroundings by a frictionless pin or connection. Frictionless just means that we're not considering friction in our calculations. 114 we will. Fun fact, I got the call to teach 114, so I'll be teaching 114 next semester. Okay. Tension on the cable rope on both sides is the same. Right, it just redirects tension 1 and tension 2. So tension 1, tension 2 should be equal to the same. I'm going to go through an example later on where I'm not going to destroy the member and the pulley. So keep that in mind when I go through the example a little bit later. Nice, nice. Okay. Learning outcomes. Create a free body diagram of rigid bodies in plane and space. Compute the reaction forces acting on a rigid body to keep it in equilibrium in plane. I don't have one in space today. Okay. Review the reactions for 2D structures. On the top we have rollers, rockers, or a frictionless surface. That will only allow us one reactionary force from the ground, pushing upward. Okay, short link or short cable. These are the same. If you have a cable, then you know it can only be in tension in the line of in its line of action. If you replace that with a short link, same thing happens. Frictionless collar or rod or pin in a slot. We did a problem like this where I messed it up and I had to go back. The only reactionary force is a perpendicular force that is normal to the line of action that the rod is or the slot is. If it is a frictionless pin or hinge, we can get a normal force and a reaction X and a reaction Y. The rough surface, I think, is the left-hand side. These two are the same. Because a rough surface, if I gave it... No, if it was a rough surface, I would have an X component as well. But then we would be considering friction, and that's not going to happen right now. Last but not least, the fixed support, where we get essentially all three reactionary forces. We get an X, a Y, and a moment about the point. Okay, shouldn't be any questions about this stuff. It's all review. Equilibrium of a rigid body. For a rigid body, all external forces acting on the body can be reduced to a force couple system at some arbitrary point O. I kind of want to segue into the quiz, but after this slide, I'll segue into the quiz. If the resulting force and couple are both equal to 0, the rigid body is said to be in equilibrium. There is a difference between a force couple system and the moment. An equivalent force couple system is different than just finding the moment. Keep that in mind for your quizzes. I saw a lot of people doing a force couple system. You don't need to find the equivalent force. Just compute the moment. You don't even need the couple. Force couple is a very specific type of problem answer. We are only looking for its moment. Okay, moving on. Uncle Bill. Not the quiz. I got the easier question wrong, but the hard problem right. It happens. Move on. Okay, free body diagram. We've talked about this before. I've drawn them every day. But it is a separate drawing. Show the rigid body and all the forces acting on it. And you need to indicate the point of application, the magnitude, and the direction of external forces, including the weight of the body, if the weight of the body is significant. And you also have to indicate the point of application and assume directions of unknown forces from reactions of the ground and or other bodies, such as the supports. It says do the free body diagram, do the free body of the diagram, but we'll skip that and just talk about it. So P, Q, and S are all going to be the same type of forces, resolving in X and Y. And they used... Yeah, these are fine. It doesn't tell us what direction they assumed is positive, but I guess I would just always assume it's a standard Cartesian coordinate system. So at A, we get an X and a Y because it looks like it has a pin here. At B, it's on rollers, so we only get a normal force. And then they add W, which acts through the centroid of the body. Okay, now we get to the meat and taters. Take 5 minutes. I'm going to draw my picture and my free body diagram. Try this at home with me. And I'll be back in just a moment. Mr. Ant Nation, thanks for dropping by, brother. Enjoy that. Okay. So determine the reaction at the fixed end. Let's go on to my view. Okay, so I redrew the picture, made a couple substitutions. The payloads are all consistent at 20 kilonewtons. I named them P0 through P3. And all the L's are all the same at 1.8. So I just named them consistently L. I included alpha, and I set that up as tan inverse of the opposite, 4.5, over the adjacent, 6. I removed point F, which made the tension in the rope from D to F here. I removed the ground, and it looks like E is a fixed support to me. So I added EX in the positive Y direction. My little picture of what I deem as positive in this setup. Positive EX in the right direction, EY upward, and moment about point E counterclockwise measured from the positive X axis. Any questions on how I got here? All right, let's get into solving. Okay, so we're looking to solve all of the...
Just for one thing.
Absolutely.
Oh, why did you remove that point F again?
Because it's part of the ground.
Oh, okay.
The cable... Oh, let me turn the picture on. Yeah, so essentially I cut out everything that was holding this structure to the ground, which included point F. And when I make that cut,
okay,
I have the tension in cable DF, which is only a 2-force member or a cable. And then I have a fixed support, which gets all 3 of them.
Okay.
All right, so let's move on to step 1. And I'm going to stop writing out Newton's second law, and I'm just going to start writing in N2L. Because I'm cool like that, I guess. I don't know. But Newton's second law. And let's sum the forces about X. And then we're going to take up EX. And then we're going to add to that TDF. And we're going to add the sine of alpha to that, resolve it. And that is all of the horizontal components. And since we know TDF explicitly, we can find alpha. Three, 4, 5 triangle. 36.86 degrees. Okay. So EX is positive, so I'm gonna let it stay on the left hand side, and then I'm gonna move TDF sine of 36.86 to the right hand side and solve for EX directly. TDF is 150 kilonewtons. Sine 36 negative, because we move TDF to the other side. The sine of this angle negative 90 kilonewtons. Okay, and all this means is that EX is drawn in the incorrect direction. I assume that it was to the right. It is not. So I will report the answer as EX is equal to 90 kilonewtons to the left. And that will be part of our answer. Now I'm going to move on to the y direction. Okay. Y direction. 1, 2, 3, 4 p knots. And they're traveling downward against our chosen positive. So negative 4 p. Okay, we're going to add EY. And then we're going to subtract TDF cosine of alpha. We'll set that up equal to 0. Okay. EY is positive, so it'll remain on the left-hand side. Both TDF and 4P will go to the right-hand side. And since they're both negative quantities, they'll now be positive on the right-hand side. Four times 20. Add to that 150 cosine of this angle. 200 kilonewtons. I don't know why I drew that character. Okay, so the assumed direction that we chose for EY is correct, and so it will remain positive, and we'll call that upwards, and I'll white out this little E or F that I was going to write here. Okay, we tracking still? What about point C? What are those reaction forces? We did not take these two things apart. I could ask you what are the reaction forces at C, and since it's rigidly attached, you could either take the moments about member AC or DE and find out what happens at C. But for this problem, they're part of the internal of member A, B, D, C, E. I thought as well maybe. No, C definitely does something. It just we're not interested in it right now, and so we have not broken apart the member into two pieces. Okay. So let's move on to the moments. And again, if you're submitting homework, don't use the side of the paper, just move on. I'm doing this because of the top-down camera and the 16:9 aspect ratio. Move on to the next page. Don't do what I'm going to do now. And so I'll start with step 2, which is technically the same as Newton's second law, but we're going to call it moments. Sum the moments about point E. Okay, and those are going to equal R cross F. But I don't know if I did it with this class, but I'm going to stop using the rigid cross product and start using more inspection on these 2D problems. Okay, so moments about E. They can take into consideration P naught first. So some of the moments about E. And our first force vector is moment arm is going to be 1, 2, 3, 4L times P naught. And since I have decided that this is my positive direction, and if I put a pin here and P naught is applied, oh, I did this the other day. So if this is E on the right hand side and P naught is being applied, this is the moment that it produces, which is consistent with my drawing. So I'm going to let this be positive still. Okay, we'll do the same with P naught or with P1. Okay, now I've taken into account all the payload. Next one I'm going to have to add, since this is some of the moments, I'm actually going to add ME. This is important for your beam calculation quiz 2 part 1, question 1. If I'm summing the moments, I add the reactionary force E, or any other moment on the page. Okay, and the last force I need to account for, since EY and EX both travel through the point in question, point E, they have a 0 moment arm, therefore do not participate in the calculation. What the horizontal component of TDF does. If we resolve this in X and Y, the Y component does not participate in the moment calculation about point E, but if I take the X component of TDF, it does participate since it travels this direction, to the right. And if I do the same thing where I put a pin at point E, and I have TDF act on this body, it is going to be going opposite of the positive direction that I've set up, which makes it negative. So the moment arm is 6 meters. I'm not putting any units here. So -6 times TDF sine of alpha equals 0. Ooh, ran out of space. Quintuple, they're neither. They're just F times D. They could be cross products, but I'm just doing multiplication. If you ever struggle with what direction these are or are unsure about the method I'm using here, you can always go back to 4L in the negative X direction times P naught in the negative Y direction, and that will equal the positive direction, since the negative times negative cancels out. And when you're doing Y cross X, X cross Y. So if you're unsure about this method and you don't want to use it, that's fine. You can go back to cross products. It'll work out just the same. I'm just doing it by visual inspection. Okay.
Why are we adding, or why are we multiplying the moment of E instead of just adding it as one of the moments separate from the moment of the tension force?
I'm sorry, say that one more time.
Why are we multiplying the moment E by the moment of the tension force rather than just adding it as one of the separate moments?
It should be just added. It might be a little unclear in this, but this says plus ME plus quantity -6.
Thank you. I didn't see the plus sign.
Yeah, so you are right. We are not multiplying that. We are simply adding it.
Okay. Thank you. I'm sorry.
Yeah, no problem. Definitely, we don't use the Y component of the tension because it technically goes through our point if we extend it. Correct. Afterwards, after I take a picture with the camera, I'll draw these resolved and show you exactly why that all works out. Okay, so we know L, we know P naughts, we don't know ME, we know TDF and sine alpha. We can solve for ME directly. So I'm going to keep ME on the left-hand side. And everything else goes to the right. So I'm going to take the first quantity, or this quantity, since it's negative, and put it first. 6 times PDF sine of alpha. Every other quantity is positive, which means it'll be negative on the other side. Algebra. When I'm copying things down like that, the brain and the mind can't talk and think at the same time. Okay. So let's substitute in some numbers and carry out the calculations. Six times 150 sine 36 minus 4 times 20 times 1.8 minus 3 times 1.8 times 20 minus 2 times 1.8 times 20 minus 1.8 times 20. Okay. Let's solve for this. Times 150 sine number, close parentheses, minus open 4 times 1.8 times 20 minus 3 times 1.8 times 20. 2 times 1.8 times 20. $1.8 times 20. 180. And the units on this will be meters, kilonewtons. And since it comes out positive, the direction we assumed in the beginning of the problem is correct. Counterclockwise it is. My plus sign does need a microscope. That is correct. I ran out of space here. This is why I should have just used a new paper, but for the purpose of this class and having an example on one page, what it does. How exactly do we add ME to the right-hand side in the first place? We never added it to the right-hand side. Yes, Katropolis, this is the whole problem. We did not add it to the right-hand side. The right-hand side is equal to 0. You also need a microscope for that one too. So on the left-hand side is all of the terms. Every moment arm times the force applied. Every moment in the problem. And also the tension on the left hand, or on the top here. That's all equal to 0. Since ME is positive, I keep it on the left-hand side. Everything else goes to the right-hand side. And the signs switch. Okay, any other questions about this one? And since I'm cool now, I can take a picture of this. I haven't figured out the workflow to getting this picture off of this camera and into the computer and on the cloud for you guys, but I'll make it happen. Why do you use -6 and not -4.5? Ah, that's actually a good question. Okay. Interesting question. Why do you use -6 and not -4.5? Yes, someone gifted subs yesterday. So let's do this. Let me do this in orange. Okay, so the question was, why component of tension first? So let's talk about tension and how I'm going to break it up into components. If I break this up into sine and cosine, the sine will give us this direction, which did participate, sine of alpha, in the moment calculation about point E, because there is a perpendicular distance of 6 meters to the point of application of TDF sine of alpha. Okay, and if I do the TDF cosine of alpha, that's that vector that you need a microscope for. And its moment arm, since its line of transmissibility goes through the point in question, is 0. It does not have a moment arm. So rather than incorporating 0 times this vector, I just ignore it altogether and I say, I'm good at physics, or I'm good at statics. Okay, and then the other question was, why do you use -6 and not -4.5? So I could also move TDF along its line of action to this point, F, and I can again expand it into these two vectors. Okay, but if I did this and moved it to this point, I would not use TDF sine alpha, because TDF sine alpha would go through the line of action, or the point in question, and have a 0 moment arm. And so if I moved TDF down to this point, I could use TDF cosine of alpha. But if I moved it here, TDF cosine of alpha would have to be multiplied by -4, or would have to be multiplied by 4.5 meters, and would also be negative because it opposes the direction we call positive, because the force applied would make this type of moment. We tracking that? That I can move TDF along its line of action? Thank you for the pogs in the chat. Smoky air is messing with me. Wilbur, do you have another question about this? What part? You can unmute and speak up and ask a specific question. Okay, no problem. After class today, I have office hours. I'll be in Discord. Anybody need the Discord link, let me know. Yeah, I had a good night's rest last night. Woke up super early, and I don't know. It's not for me. The smoke and the orange sky. I got invited to a Facebook group yesterday. Literally, the only thing we post in there is orange sky photos and orange, like, Bay Area photos that are orange. It was nuts. Absolutely nuts. Okay, let's go back to the lecture slides. Reading for next class. Read chapter 4. How was chapter 4? Was that good? Oh, man. It's all bad. Photographers having a field day? Oh, man. I saw some absolutely stunning photos yesterday. Absolutely stunning photos yesterday. Okay. Welcome to Lecture 7, Equilibrium of Rigid Bodies, covering Chapter 4. Dalton! Your video gets chosen today. We're going to watch a recount of the first flight. Woohoo! Okay, pause that. Move this. Pause this. Here. Set it up. Boom. Get me out of here.
Flight was a success, I'll say that, because we took off. The first flight was a success, I'll say that, because we took off and we landed. But there were some problems that we encountered and some things we discovered that needed to be fixed. But let me go back just a little bit. The airplane is unstable in pitch and yaw. It can't be flown without the assistance of computers. At the lower speeds, it's about neutrally stable, which is almost flyable. One of the bits of information that goes to the computers to help fly that airplane is the air data that goes in the probes on the front of the airplane. And the engineers were afraid that the vibration of those probes on takeoff and in turbulent air might send vibrations to the flight controls and cause them to oscillate. And so therefore they did not want to use the air data on the initial takeoff. So what we did was we put a bunch of lead in the front of the airplane and made it positively stable, thinking that I could manage the airplane. It was still not real stable, but it was stable enough that we felt that I could fly the airplane satisfactorily up to 10,000 feet and then turn on the air data information to the computers so that if it did cause a problem, there would be plenty of room between me and the ground to get those things turned off again and bring the airplane back. That was the plan, and that's what we did. We took off, ballasted with lead in the nose so that it was slightly stable on takeoff, which was fine. The rotation and everything was good in pitch. It was that the fact that the airplane started to yaw, and it went out, I believe it was 6 degrees to the left, and then I tried the rudder to stop it, and it didn't respond right away, and then it slowly came back the other way and went out to around 12 or 13 degrees the other way, and that's very uncomfortable in an airplane to feel like you're skidding sideways. And so I realized that this thing wasn't acting the way we expected to act based on the wind tunnel and simulation that we'd done. Actually, I had 3 switches for pitch, roll, and yaw over on the left-hand console, and the yaw switch I had extended because that was the most critical one. And I turned on the air data so that it would come through the probes and go to the flight control computer to help me fly the airplane. And it did. It worked fine. There were no vibrations or anything like that. But they got turned on a lot quicker than we planned to do because we were going to go to 10,000 feet to turn them on. Based on that information, we realized that the fins on the airplane, the tail fins on the airplane were considerably too small. The wind tunnel data, I don't know how a mistake was made. Somehow, I believe I heard that they didn't take into full account the sting that the pole that you put an airplane in a wind tunnel on contributes to stability. And I'm not sure that's the case. At any rate, they came up with a figure that they said we were going to be more stable than we really were. So the fins were too small, and that was the big discovery on the first flight. And we flew the airplane 6 more times in a very limited flight envelope while they were building a new set of fins 50% bigger that were put on the airplane. And from that point on, we had the proper amount of stability. That was the big thing learned on the airplane. The minor problems that we occurred are not minor, really. We had overheat in the tailpipes because the tailpipes were rectangular, and in the corners heat builds up, and they were reaching limited temperatures. And we also had the canopy unlock light that came on, and that was of concern because if the canopy had come off, you get a face full of wind, and it was marginal about whether you could land the airplane or not. And the other thing was that we heard a big thump and that was the blow-in doors, which were spring-loaded and activated so that it gave enough air for the airplane on the ground, enough air to the engines to run properly, and then as you accelerated, more air came in the inlets, and then the doors would spring-load shut, making the airplane stealthy, because you can't have openings in the airplane and be stealthy. And when they slammed shut, there was two very pronounced thumps that I hadn't anticipated, scared the heck out of me. But there was no indication in the control station nor on my instruments, so we continued on with the flight. The flight was only 15 minutes, limited by the temperature in the tailpipe. And that was basically the first flight, yeah.
Thank you very much for that, Dalton. Go back here. Small engineering mistake, and this dude is up there skidding sideways in the odd direction. We're just drifting his airplane. Kind of unsettling. Right. Good video. Yeah, this was kind of dope. Where do we submit videos? Grombro's got it on Canvas. There's an assignment that you can put a link in. Absolutely correct. There's like, I think I have like 7 or 8 submissions, so I have to like watch them and like see which ones is the best. But if you have a cool video, submit it. I watch them. I watch them in 2x speed. So thank you for submitting that. I'm moving on. Wait a minute. I already opened up quiz for you guys. I don't know why I included this slide again. Right, this class already has access to the quiz?
Yeah.
Okay, and it closes tonight at midnight. So you got a little over 12 hours to get it done. Some of you have not mastered the concepts in quiz 1. I sent out the emails to those affected. If you passed it, don't worry about it. If you're on quiz 2, don't worry about it. Okay, this is where I would split everybody up into groups at the tables and have you guys draw free body diagrams together, but everyone's at home, so draw a free body diagram by yourself. We're not going to solve anything. We just want to see if we can test what things we want to test your understanding of the reactions. And so we're going to draw a free body diagram of member CB. Includes the pulley, A, and B, the wheel at B. It should be in quizzes, Van Halen. Val Halen. You guys should be able to see it because I've already graded some quizzes there. Can someone ban that account? Nice. You don't need to delete, you can just ban. Directly to ban! Okay. Draw the free body diagram. I've already started on mine. I'll be back.
Which member was it? Again?
Member CB is is one piece of L. So don't take off the pulleys, don't take off the wheel, but you have to separate the pin from the ground and the wheel from the ground, as well as the tension force from the wall. So we're cutting off everything that is attached to this black line with brown gradient.
Okay. Thank you.
Uncle Bill, yeah. And I mod all of my students, so when you ever see stuff like that, just ban it. We don't need it in this class. Okay. How did he beat me in an 86? I guess I have to look at the link to know. Want to become an aerospace engineer? Buy planes, a degree, and internship at bigfollows.com. Guys are trolls. Okay, let's show you what I have done. So I just redrew the picture in the top, retained all the information, 75 newtons, 18 centimeters, 10 centimeters at the bottom, 3, 4, 5 triangle, 3 centimeter diameter or radius on the pulley at C. In member CB, I guess I should add the distances again. Okay. So member CB. I should also tag those. Okay, since I cut off the wall on the right-hand side, I made a cut here, which means I have a cut in the tension. I know that it's a pulley and it's redirected, 75 newtons. Because of the payload here. I did not solve for alpha because we're not gonna calculate anything in this problem, so I just left it as 3, 4, 5 triangle. The 75 newtons stays the same. I could add the 3 centimeters, but it's gonna dirty up the drawing even more. So the big points of this problem are gonna be A and B. A is a pin, and so it will get an AY component, force in the vertical direction, an AX, force in the horizontal direction, but it cannot accept a moment. If you applied a moment to this pin, the structure would just rotate. There's no resistance by the reaction itself. So no moments for the pin. And then at point B, it is a roll or frictionless roller, and so it only gets a normal force of a BY. If it cannot accept an X component because let's just say that thermal expansion was a thing. If this member thermally expanded, B would just roll out of the way. Same thing if I applied a moment to that point, the structure would just rotate. And if it doesn't rotate, then those forces would go through AY. Any questions on why I drew the free body diagram like this? Pretty simple example. Let's move on to another moment calculation problem. Okay, we just talked about this. I don't know why I repeated the slide. Ah, this is why. The second part of the statement. So we've done the top part many times over again. Some of the force in X, Y, and moments. I collectively call this Newton's second law in the steps that I'm trying to solve. But at some point in the future, real soon, we're going to get into a truss structure where you will not be able to simply solve for what you're looking for immediately and explicitly right off the bat. It'll be statically indeterminate, which means you have more variables than you have equations. And what you want to do in that situation, if you solve for X, Y, and Z, or X, Y, and moments, and it's statically indeterminate, you have 3 equations, and you have 4 unknowns, 5 unknowns, whatever. What you can do is add an additional moment equation. Okay, you can't add additional equations. So the 3 equations of equilibrium cannot be augmented by additional equations. So if you think up a plan of P is equal to negative Q times the distance C between them, like, none of that stuff works. Don't do that. But you can replace them with another equation of equilibrium. Trust the process. Okay, so for example, in this problem, what I'm thinking of when I look at this problem is that if P is unknown, P, Q, and S are unknown, I'm going to take a moment about point C, because P does not participate in the moment calculation about point C. Nor does one of the A reactionary forces. Q, S, reactionary force at B, and 1 reactionary force at A all participate. But then once I get that equation, I can then take another moment equation about point D. And then S won't participate, while the other ones will. And so I have more independent equations to solve for more variables. That concept you have to wrestle with a little bit, and you're going to have to use a little bit of creativity to understand where you should be taking moments about to eliminate the most amount of unknown variables. That's what this slide is all about. Okay, next example. This one's fairly short. So a gardener using a 60 Newton wheelbarrow to transport 250 Newton bag of fertilizer. What force must she exert on each handle? Go ahead and draw your free body diagrams while I draw mine. And we'll reconvene in just a moment. Okay. I didn't even get to hide my screen. You guys watch me draw that. Okay. So since I don't need to switch over, I redrew the problem here. I didn't mark A. And the only thing I added was 2H, because the problem asks, what force must she exert on each handle? There are 2 handles on a wheelbarrow, and I named each one of those forces H. And since we're on a side profile view, I called them 2H. Okay, I redrew my rigid body with the reactionary forces, and in this case it's only the wheelbarrow touching the ground, and since it's a roller, we're assuming that a wheel is frictionless. I guess she's just lifting, she's not pushing, even though it looks like she's walking. Lots of assumptions in these pictures. But we only get a normal force AY for the wheelbarrow. Weight stays the same, P stays the same, and 2H, 2 handles. So our knowns going to be weight equal to 60 newtons, payload equal to 250 newtons, and we're looking for H. Should be reported in newtons. Okay, so fairly simple moment equation here. Sum the forces about point A. So the moments about point A are going to equal, since we're taking about point A, the reactionary force at AY does not participate in the calculation. First one that does is W, and that'll be a distance 0.15 meters. These are in meters. Microscope for those. Probably should have drawn it bigger. Okay. 0.15 meters times weight. Okay. And since I have decided that this is my standard coordinate system, W relative to A provides a negative moment, and so this will be a negative quantity. It will add to that the next moment, which is going to be brought about by point P. 0.15 times, or plus 0.15 is going to equal 0.3 meters times P. And again, that will be negative for the same reason as before. Produces a clockwise moment about point A. And then we have 2H. Moment arm is 0.3 plus 0.7, which will give us 1 meter, times 2H. And since this is going to produce a positive moment, or a moment that agrees with our positive denotation, this will remain positive, and this will all equal 0. Okay, so now this quantity is positive. We'll retain it on the left-hand side. So we'll draw that first. These two quantities are negative. We'll move those to the right-hand side, and they'll become positive. And I'm going to substitute numbers in here as well. Okay. Those out over here. Let's carry out the calculation. And while I'm carrying out the calculation, the 2 on this side is a scalar quantity, and so I'm just going to move that underneath and divide the entire thing by 2 at the end. So 0.15 times 60 newtons plus 0.3 times 250 newtons. Enter. Divide by 2. So vector H is going to equal 42 newtons. And since I assumed that when she wants to lift the wheelbarrow, her force will be in the upward direction, I was correct. So the positive value means that it is indeed going upward. So, advantage wheelbarrow. Right, you have a 60 Newton wheelbarrow and a 250 Newton bag of fertilizer. The only force you need to put in is 42 newtons per handle. A grand total of 84 newtons total to lift a 250 bag, 250 Newton pound of fertilizer, and a 60 Newton wheelbarrow. That's the good stuff. Mechanical advantage. Any questions on this problem? Oh, I'm putting that away. All right, let's move on. Is this my next example? I have a couple in here that if you want to try, I have solutions for. Anytime I use a wheelbarrow or whatever, I literally have to say mechanical advantage. It's annoying. There are a couple situations where I say that as well. Okay. So, example 4.22, part A. Doing pretty good on time, too. Okay. The rig shown consists of a 1,200-pound horizontal member, ABC, and a vertical member, DBE. So remember before when I said we were not going to consider weight because the problem didn't give us weight? This problem did tell us how heavy member ABC is, and so it's going to be important for us to incorporate that numerical value, 1,200 pounds. Okay, and a vertical member DBE welded together at B. The rig is being used to raise a 3,600 pound crate at a distance of x equals 12 from the vertical member DBE. If the tension in the cable is 4 kips, what are kips? Type in the chat. Tell me what kips are in the chat. Determine the reaction at E, assuming that the cable is anchored at F. Okay, so it wants us to determine the reaction at E. Nailed it. Kilopounds. So this is actually 4,000 pounds. Brian, yep. 1,000 pounds. Yeah. I agree with that. Breaker bar and rusted bolts doesn't matter how much torque you apply when a bolt turns into a pin. Yeah, but at least it's free, because you can just pull the pin out. Radiant kips are thousands. So the tension in the cable is 4,000 pounds. That's what this tells us here. Okay, you know the deal. Draw your free body diagram, and I'll be with you in just a moment. Bye-bye! Okay, I'm back. Rotate this to give you a good view of it. Okay, top picture is just a redrawn. The bottom is my free body diagram, which I will label. And I guess I can call this, I don't know, AD. It doesn't really matter what you call this. Okay. So, question is asking us the reactions at E. So, based on the picture, I assume that this is a rigid connection, which means we have an EX component, an EY component, and a moment about point E. And again, I assumed a standard Cartesian coordinate system. Positive, positive, positive. And since I removed the ground, I also cut off point F, which means I have a tension in the tension from C to F. Do I know tension? I do know. Okay, let's populate our knowns. TCF. Okay, when I populate this list, the problem statement gives us pounds and kips. It's looking like kips is going to be an easier system for me to work in. So I'm going to go with kips. Okay, it's case here TCF. Payload. 3.6 kips. And the weight of the structure, or weight of the beam, is 1.2 kip. Okay, I made the substitution for x, because there's a lot of other values that I left in there as numerical values. You can substitute them for variables, but sometimes it gets a little more trouble than it's worth. And so leaving the dimensions in there, if you copy dimensions down incorrectly like I did last class, things happen. It's not the end of the world. My watch just told me I have to stand. Cool. All right. So let's start with Newton's second law. And again, I'm going N2L for Newton's second law. And let's start with some of the forces in the x direction. Okay, so in looking at my drawing, I see that I only have one vector in the x direction, which is going to be EX. So EX equal to 0. Done. Nothing else participates in the x direction, and so I know that one explicitly. Okay, let's move on. Some of the forces in the y direction. Okay. Starting on the left, I have P acting in the negative y direction. We'll add a negative there. A negative W. I have a positive EY. And I have a negative TCF. And all of that will equal 0. So I know P, I know W, I know TCF. I can solve for EY directly. So let's keep EY on the left-hand side. And I'll move everything else to the right-hand side. And everything is negative. So when I move it to the right-hand side, everything will then become positive. So P, 3.6 kip. Plus weight, 1.2 kip. And TCF, 4 kip. And so EY will equal 4 plus 1.2 plus 3.6, 8.8. And EY came out positive, which means this is the correct direction. Upward. Any questions on this? Move on to our friends, the moments. Okay, again, if you're turning something in, don't use this space. I'm going to use it because of this format. And again, we'll call it step 2, even though it's not really. Some of the forces, some of the white out. Some of the moments. About point E equal to 0. So let's start with the P direction. And so the moment arm is 12 feet. We're going to multiply that by P. And now this is where the positive and negative comes in again. If I am at E and I apply force P, it is in agreement with the positive direction, so it will remain positive. Weight, moment arm is going to be 6.5 feet times W. It's going to remain positive for the same reason. ME participates. So I'll leave room this time. ME by itself, no moment arm or anything. I just add it. EY does not participate because it goes through. It has 0 moment arm. Same with EX, 0 moment arm. Last one is TCF. And the moment arm on TCF is 3.75 times TCF. And by the same logic, if I have a pin at E and I apply TCF downward, it does not agree with the positive moment direction that I've defined previously. So this one will be negative. And that will all equal 0. All of a sudden, the stream beat got super hard. You're just like, I don't know if I really like it for this class. Okay, so in examining our equation, we know P, we know W, we know TCF. We can solve for ME directly. ME is positive, so we'll remain on the left-hand side. Okay, this one is negative, so I'm going to move it to the right-hand side first, and it'll become positive. These two quantities are positive, and so they'll go negative. Let's substitute in values and solve. TCF for KIP. $12 feet by P, 3.6 KIP. Plus negative 6.5 times W. And we'll turn that hard music back on. I don't know. Okay, let's solve for this. Let's calculate. $3.75 times 4 plus I'm missing a negative there. Need a microscope for that one too. Negative 12 times 3.6. Negative 6.5 times 1.2. Close parentheses. Negative 36 foot kips. Okay, and so the answer comes out negative, which means the assigned direction when I initially started the problem, ME, is not correct. So it does not go in the counterclockwise direction, it goes in the clockwise direction. So the answer reported will equal 36 foot kip clockwise. Oops. Okay. So intuitively, that kind of makes sense, right? If I have tension in the cable, 4 kip, but I'm lifting something and my beam weighs 4.8 kip, it would seem like this structure would want to rotate this direction, but it doesn't because there's a moment about point E that opposes that force in the opposite direction. Are we happy with this? Lecture 7, example 3, 9, 10, 20. Wow, come on. Focus. Thank you, Jose. Getting that pog in the chat. Rashad, thank you very much. Okay, it's 12 o'clock. I don't have enough time to get through the next example. Let's see what we got in the slides here. I don't know what happened here. Oh, apparently I'm supposed to take a break somewhere in there. I'm bad at planning the breaks when they're not, when I don't finish an entire lecture. Okay, I think this is the next problem I want to do. This is an equilibrium problem in 3D. My brain hurts understanding what happened to this file. Okay. If I want to sum problems in equilibrium in 3D, I have the same equations, x, y, and z, but I also have moments in 3D about any point you'd like. So on the left-hand side, we have 2D scalar equations, the ones we're all familiar with. In 3D, we have 6 scalar equations that we can use. But it's not quite the truth, because earlier we talked about how we can substitute additional moment equations to get more equations, more linearly independent equations out of the problem. But this basically shows you have at least 6. You have x, y, and z, and then you have the moment about axis x, the moment about axis y, and the moment about axis z. And when you report answers in 3D, this is generally what you will report. X, y, and z, and then moments about axis x, axis y, and axis z. Okay, more reactionary forces. The ball just means we have a normal force, top one. Cable gives us the same cable. That one's not new. Roller on a rough surface or a wheel on the rail will give us 2. So it'll give us the normal force and it'll give us an FZ. But again, if we give it a Y, well, in this particular example, the second line, if we give it an X, the roller will just roll. But if we give it one that comes towards us out of the page, it will provide a reactionary force there, and it'll also provide the normal force going upward. Okay, and rough surface. Again, we're not going to take this one into consideration. The ball and socket is an interesting one. So if it says ball and socket, we get 3 force components, X, Y, and Z. It cannot accept a moment in any direction. Because if you think about a ball and socket joint, if I rotate it, the rod will be able to freely rotate in the ball and socket. No matter how I give it a twist, it will accept that, and it will not provide any reactionary forces. But if I physically try to translate it downward, it will oppose that. If I physically try to translate it left, right, or any direction in that plane, it will also oppose that, and that's why we get 3 force components there. These ones get a little more in the weeds. You can check these out, and if our problem warrants them, you can take a look. If you have any questions on these, let me know. But they're pretty specialized in what applications they are. But we will probably go through at least one of these examples through the course of this class. One example in each of these reactionary force types. Again, I don't have time for this problem. Another problem you can solve at home. Oh, I didn't give you the answer here. Anyways, read chapter 4. So 12:05, we got 5 minutes left. That's all I have for everyone today. If you want to hang out, you can hang out. But I'm going to cut it off at 12:10. So if you're in the Zoom chat, you're free to go. If you're in the Twitch chat and you're subscribed, we don't. Our emotes didn't get approved yesterday. Didn't get approved yet. Of course. You're welcome. You're welcome. So for those of you guys that are following along in the Twitch chat, I had some maniacs yesterday that were subbing with their primes and gifting subs and doing a bunch of dumb things that I don't recommend you guys doing. But we did get up past 15 subs on the channel, which means we unlocked a second emote slot. And if you go to the Discord, you can actually see the first emote slot emote that I... Can I make you some emotes? Yeah. Rai, love you, buddy. Thanks for coming out, man. Appreciate it. Would you grade my makeup quiz? Yeah, I'll get to that today. Valhalen. Yo, another subscriber. Pertupo, yeah, that's the 154. Yeah, absolutely. Valhalen, you must be one of the ones that did not submit the quiz, preliminary topic makeup quiz. Go ahead and complete that one, and I'll grade them tonight. Rai. Send me a message, and I'll make sure that you have enough time to take your quiz too, since it is being closed. Okay, then I'll make sure to grade these. So, do we need to do the makeup quiz? Yes. You do need to do the makeup quiz and pass it before you can see quiz 2. I don't use my Prime subs, so might as well. Hell yeah. Appreciate that. So if you guys want, join the Discord, and I'll make sure that your status is updated and ready to go. Thanks, Wilbur. Take care, brother. What else am I going to do? Listen to CityFlex complain about his alt being diamond? He's got 2 diamond accounts now. Right. Have you ever seen Flex's desktop? Thanks, Tess Kumar. Bye-bye. Today I have office hours, so I'll be in Discord for another 2 hours. You can join the Discord chat. I'll be in there for the next 2 hours. Alright, we're about to get nerdy in this mother right now. Right, this is a giant mouse pad, brother. It's Valorant themed. Huge, too. Alright, anyways, 2 minutes left. Oh, actually, Fry, I can show you what it looks like. Oh, it's kind of cut off. But this is the setup that I'm working with here. AE pubs. Yeah, I play Valorant, Lopez. This is the setup. This is where I bring you guys your lectures from. This is how I do it. Ooh, you got lights? I got green screen too, brother. Okay, 12:10. Anything else? We're gonna cut off the Twitch recording in less than 1 minute. Yeah, Fry, it's a standing desk. I don't even own a chair. Uncomfy? Bro, I'm trying not to live my life comfortable. Comfortable is the enemy. Plus, I can do weird things like this, like, oh. I'm back. Okay. 12:10. I'm out of here. Thanks for stopping by, Twitch viewers. Appreciate the support. The love and support I've seen from the random Twitch viewers is kind of awesome. So if you like it, I stream every day here, 10:30 to 12:10 p.m. Pacific Standard Time. Stop out. Talk to you later. Bye-bye.